We are Group 16. My name is Leila Hertz. I'm working together with Shreya Agrawal, Shapiro, and Isabelle Stern, and we've been working under the mentorship of Dr. Shi, who is a professor here in the ISE department. For the next 8 minutes, we're going to talk to you about our senior design project, which is focusing on improving the state of charge in lithium batteries. So I'm first going to ask a question, and we'd love for you to participate by using the reaction button at the bottom of your Zoom screen. So how many of you have experienced being outside on a really cold or really hot day, and your phone says you still have 20% left of charge, and then suddenly it dies on you? So I'm seeing some reactions. If this is something you can identify with, so can we, and this is what we wanted to find a solution for in our project. So there's a common problem in not only phones, but laptops, medical devices, and drones, where the battery will die unexpectedly in hot or cold weather. Why does this happen? Well, this is because there's an algorithm that is most commonly used in these devices for estimating the state of charge. And this algorithm does not take into account temperature. So state of charge, that's a term you're going to hear a lot throughout our presentation. And what state of charge, or SOC, means is basically how much juice is left in the battery. So the vision for our project, we wanted to come up with a solution for this problem. And to do this, we wanted to create an improvement to that algorithm that is currently used. And we'll create this improvement by accounting for temperature. Some of the advantages to this are increasing the battery reliability of these products while still maintaining the efficiency that's inherent in the algorithm.
So the relationship between temperature and state of charge has already been extensively researched and studied. So we already know that temperature impacts state of charge in lithium batteries. And there's also many established ways to estimate state of charge already. And some of those methods already account for temperature. But we're focusing on a very simple state of charge estimation algorithm that's very commonly used in those small and portable devices that Leila's talking about. And this state of charge estimation algorithm is based on only two parameters. That's the current that's flowing through the battery and also the battery's capacity, which is basically how much charge the battery can hold. This estimation algorithm is referred to as Coulomb counting. And for the rest of the presentation, when we talk about estimating state of charge, we're talking about this specific method of doing so. So that's where we contribute. We are going to add a temperature consideration to the Coulomb counting algorithm in order to, like Leila said, improve the accuracy of the algorithm while maintaining that simplicity that makes it so useful in these small applications like in phones, laptops, drones, etc. So how did we make our improvement? So we obtained some lithium ion batteries from the lab, and we created an experimental environment where we could discharge the battery from 100 to 0% and collect data on the battery's discharge. We identified the relationship that exists between environmental temperature and battery capacity and incorporated this relationship into the already existing Coulomb algorithm to make that improvement to the estimation. So just to go into a little bit more detail about what we did exactly, we built a truggy car through which we could put a load on our battery and drain it from 100 to 0%. We integrated current, voltage, and temperature sensors into the car so that every second we could monitor these parameters in the battery as it discharged. And you can see in this picture on the left here, it looks just like a jumble of wires on the car, but it's got our sensors and they're hooked up to our laptop, feeding us this information every second. And on average, we obtained about 1,300 points of data every time we discharged the battery that we could use to improve our estimation. So in this video, I'm not sure if the quality is good enough on this big Zoom call, but you can see the car is running. That LCD in the middle of the car is reporting the current through the battery at every time step. And we've got the other sensors in there too, hooked up to the computer. And also through this slide, we wanted to show you guys that we wanted to test our environment in different temperatures. So we made sure to get indoor around 70° Fahrenheit temperatures and also tested in the cold to see temperature's impact on our experiment. So now we're ready to analyze this data that we've been telling you about. But first, Shreya is going to talk about how we needed to adapt our data analysis to the limitations brought on by the COVID-19 pandemic.
So one of the biggest limitations that we faced was the lack of lab access. With lab access, we would have been able to complete our own battery capacity testing. To combat this, our team members took data from the manufacturer ProTech and computed our own battery capacity and temperature model, which I'll speak about right now. So on this capacity versus temperature graph, what exactly do we see here? It's a straight horizontal line. The capacity isn't changing whether it's getting hot or cold. This is what the original Coulomb counting algorithm takes into account. That capacity parameter doesn't change whether your device is in a hot or cold environment. Conversely, this is the model that we created based on the manufacturer's data. As you can see, capacity is constantly changing with temperature. This is what we implemented in our state of charge estimation algorithms that Eric will now speak to.
Yep, so in order to go ahead and gauge the success of the algorithm or the equation that Shreya just introduced, we had to line it up to our base model, which you can see here in blue on the state of charge versus runtime graph. This blue model represents basic Coulomb counting method and with no consideration to temperature's effect on capacity. And here, the red line is our model, taking into account the adjusted capacity model. And from this graph, we see that it worked because the endpoint of that graph is closest to the x-axis or 0 when the battery's dead at the end of that run. So we can see that since the red line is lower than the blue, our methodology worked. Just how much did it work? We actually improved the base model by 0.18%, which equates to 1 second of state of charge. So this shows us that our model worked, and maybe not by as much as we'd wanted it to, but since we showed an improvement in every single run that we ran, it shows us that our model works. So not satisfied with these results, we went forward and conducted created another temperature versus capacity model from external data conducted by an experiment at the University of Munich. And this model is more robust and allows us to get a better idea of what we would be able to come with given lab access and all those resources that come along with it. This model improved the baseline by 2%, which equates to 10%, 10 seconds of state of charge. And these results, all in all, support our prediction that state of charge estimation will improve with our adjusted capacity models. So in conclusion, our group believes that given lab access, we would be able to create a model that would allow us to increase past greater than or equal to 2% off the baseline model of Coulomb count. So all in all, we've implemented a temperature consideration into one of the most commonly used state of charge estimation algorithms. This will help users like you know a little bit sooner whether your battery will die or not on adverse weather conditions and hot or cold days. So thank you all for joining us. We want to give special thanks to all the mentors that helped us out on the way and open the floor to any questions you may have. Thank you.